we want to see what happens when we have energy that's dissipated in a problem. Up until now, we've assumed that friction hasn't been very significant. So sometimes that won't be a good assumption, and we'll have to take into account friction. In this question that we tried last night, you had a wily coyote from an old cartoon, if you remember it or have seen it, was shot straight up in the air with an initial velocity of 50 meters per second. So we solved the problem with assuming that all of the kinetic energy was transformed into gravitational energy, and at his maximum height, he had zero kinetic energy and had stopped for an instant in time. In part B, we're going to assume that there's some air resistance or friction, and that air resistance is going to reduce the maximum height so he won't go as high. And to do that, we'll account for that air resistance in our dissipated energy. So that's one way to deal with frictional forces, especially something complex like air resistance. So let's do our diagram. We put our system in the circle here, and we'll do our initial and final. So our initial will be when he's at the ground height. And he's just been shot up. And then our final will be maximum height. So the types of energy that we have at ground height is no gravitational potential energy, because that's our reference. We'll set that to be our reference height. Our elastic energy, we don't have a spring or an elastic, so that will not be, we won't take that into account. But Wiley will have lots of kinetic energy, so we'll do 4 bars of kinetic energy. Sorry, I forgot to fill this in. So Wiley Coyote, we want to include the Earth in the system, so we'll keep track of the energy with Wiley Coyote and the Earth. We're going to add air in, so that's an internal energy that can be dissipated. And then in our final energy, it's the Wiley at max height will have stopped for that instant, so there won't be any kinetic energy. That energy will have turned into gravitational potential energy, but some of that energy is lost. It's dissipated due to air resistance. So instead of, normally we'd have all of the gravitational or kinetic energy going to gravitational potential energy, but in this case we've had some of that energy lost to air resistance, and the rest will go into gravitational potential energy. So to solve this one, there is one thing that we will have to do is, because it says that 20% of his initial kinetic energy was lost due to friction, to be able to find out how much was dissipated or lost due to friction, we're going to have to actually find out what that initial kinetic energy is. So this is going to be a little bit of a different, normally we just sub right into our law of conservation of energy, but we will have to actually know what that kinetic energy is. So we know initially Wiley Coyote is traveling with a speed of 50 meters per second. His mass is 20 kilograms. So, and we also know G. So we can find, if we know Wile E. Coyote's initial velocity, we can find his initial kinetic energy. So let's look for that initial kinetic energy first, and then we'll sub into our law of conservation, where our starting energy has to equal the ending energy. So I'm going to start by subbing in 1/2 times the mass times velocity squared, initial velocity squared, which is 50. So this will give us 25,000 joules. So we actually haven't used joules a lot because we've been taking out of our mass, but if we do have kilogram meter squared per second squared, that's joules, or Newton meters. The next thing we want to do is find the dissipated energy. It's going to be 20% of that. So our dissipated energy is 20% of that EK, or 0.2 times EK. And this will give us 5,000 joules. So once I know my dissipated energy and that initial kinetic energy, I can use my law of conservation of energy, where I take all of my initial energies, sub them into here, all of my final energies, and sub them into here. And we can see how high he will go based on our gravitational potential energy. So let's sub in our initial energies. It's only EK initially, and then after we have both EG and dissipated energy. So I'm going to solve this a little bit differently. Since we already know our EK and our dissipated energy, I had to find EK to find that dissipated energy. I'm just going to rearrange to solve for EG. So that will be the kinetic energy minus the dissipated energy. Which is going to be 25,000 joules minus 5,000 joules. So my final gravitational potential energy is going to be 20,000 joules. And I also know that gravitational potential energy is equal to mass times the gravitational field strength times that final height. And I can divide, if I want to solve for that final height, I can divide both sides by mg and solve for the final height. I'm just going to use Newton meters instead. That's one of the equivalent units for joules. And then divide by my mass, which is 20 kilograms. And also divide by my gravitational field strength, which is 9.8 newtons per kilogram. So I will end up with my kilograms canceling out on the bottom because I have kilograms and per kilogram. On the top I have newtons, and on the bottom I have newtons. And I should have meters as my unit, which makes sense since I'm finding height. And my final answer is 102. So Wile E. Coyote's height is a little bit less when some of the energy is dissipated. It's not all converted to gravitational potential energy, so he won't go quite as high. And that's how we deal with our dissipated energy. It just is part of our final energy, and we can account for it in our law of conservation of energy equation.